Okay, so before we go into 11.5, it's actually on your notes though, at the top of the page for 11.5, I just lost my page, so we're looking at that one, is a list of everything we've done so far. It lists geometric series. How do you know when you have a geometric series? There's a common ratio in R. You're always multiplying by the same thing to get to the next term. P series? What's a P series?
Raised to some power.
Raised to some power, let's be a little more specific. In denominator, you're right. So you have 1 over n to some power in a denominator. That's a P series. When do those P series converge? P is, that's what it diverges. See, greater than 1 it will converge. Because remember, we want things here to be small as possible. That's tiny numbers are going to help it converge. So a larger exponent makes this fraction smaller. So that's a P series. What's the harmonic series? 1 over n without that P right there. P is equal to 1. What do we know about the harmonic?
It diverges.
It diverges always. What's the divergence test tell us?
That if an is not equal to 0, then it diverges.
If what's not equal to 0? I
The
didn't hear what you said.
if an,
AN?
yeah.
So AN is the general term. So it's not that we want that to be 0, but we
It's not
want the
equal.
limit in the long run.
Oh, okay.
If this limit is not 0, then your series diverges. What happens if it is 0?
It's inconclusive.
It's inconclusive. The divergence test is called the divergence test. It's not called the test for convergence or divergence. So some of you on your lab that just passed that wrote, oh, it equals 0, so it converges. That is not true. My counterexample for that is this one. Tell me about this series. It's the harmonic series, and we know it diverges. What's the limit as you approach infinity of that? 0. The limit is 0 for this guy. Your terms are approaching 0, but it still diverges. So the divergence test only says if it's not 0, it will diverge. The only way you could possibly converge is if the limit is 0, but that doesn't mean it's a guarantee. Integral test. That's where we just turn it into a function and integrate from 1 to infinity or 2 to infinity. You're going to do that?
You said a series is convergent if the integral is convergent?
Right, so the integral and the series would behave the same. Would they both converge or both diverge? And the comparison test and limit comparison we just talked about. So far, so good? Okay, here's the good news. 11.5, alternating series test. Alternating series are the easiest ones we're going to see. So here's a nice little short, sweet series. A short, sweet test. It's our new best friend. It's that easy. So an alternating series is exactly what you would think it is when you say the word alternating. It could be written something like this. It has some part here that makes it alternate, so it goes negative, positive, negative, positive. The exponents on here might change. It might be, just n or n plus 1 or something. And then this part over here is some positive number. So you end up with plus and then minus and then plus and then minus. An example might be what I call the alternating harmonic. So this part is positive. This part makes it alternate. What would the first term be? Negative 1 over 1, right? Negative 1 to the 1, 1 over 1. What's the next term?
1.
Next I'll have to plug in 2, careful. So I plug in 2 here, that's positive, but I have 1 over 2. Would be 1/2. See what 1/2 came from? Plug in 2 in here and here. What's the next one? Negative 1/3. Positive 1/4. Negative 1/5, so forth. Plug it in, n equals 1, 2, 3, and so forth. So we know the harmonic series, if this wasn't here, we know that one diverges. It just keeps adding and adding and it blows up, goes off to infinity. But what happens here? Like, let's do partial sums. What's S1? The sum of the first term? Negative 1, right? What's the sum of the first two terms? Negative 1 plus a half, that's negative 1/2. So now I have negative 1/2. If I add a negative 1/3 to that, both negative, so that's negative 5/6. Negative 1/2 minus that one. And then if I add another one, now I'm adding 1/4. I'm doing fractions in my head, see if I can do that. Hold on, there's 12. I think it's negative 7/12. Someone can check that if I'm wrong. Everyone all right with this notation? Just adding that many terms? What happens to these sums though? If I add one term, it's really kind of boring. What are they doing? Approaching 0? You think so? I don't know, I don't think it is. Because this one was negative 1, this one's negative 1/2. How does this one compare to those two before it?
It's bigger.
It's bigger than this one, but smaller than that one. It's in between those two, right? And then when you get to this one, it's actually in between those two also, right? It's in between negative 1/2 and negative 1. And as you add a little bit more, what happens, we keep adding and subtracting a little bit, it just never, it's kind of trapped between those first two terms, right? Because it can add a little bit more, subtract a little bit more. That visual you have on your graph shows you what happens to the SNs. If you start here, the next time you add something, it goes down. Then you add a little bit more and you subtract, and you end up adding and subtracting, and you will have to converge to something, because you get a higher y value, a lower y value, a higher sum, a lower sum, higher, lower. There's no way for it to diverge, because every time you add something, you get to subtract something. And you add a little bit more, subtract a little bit more. And the important thing is that we're subtracting a little bit. Like if I was adding 5 and then subtracting 6, and then adding 7 and subtracting 8, those would be getting more negative or more positive. But because these numbers without the signs are getting smaller, it kind of traps me in between those first two terms, and I can't add and subtract enough to get out of there. So that's what the alternating series test is going to tell us. You only have to check two things. Once you recognize that it alternates, all you have to check, so just about the middle of the page, is that the limit as n goes to infinity of the part that's positive, if that part's approaching 0, so in this case, this part is approaching 0, right? If that part's approaching 0 and they're decreasing, then the series is convergent. And minus 1. This was 10, this one's fading pretty quickly today. So if your terms that aren't alternating are getting smaller and heading towards 0, you're guaranteed a convergence. And if they aren't doing that, you're guaranteed a divergence. This is the nicest one where it's either clearly convergent or divergent. And all you really have to do is check for decreasing and heading towards 0. Ever understand why? Why that works? Question on why? If you don't understand why? Or you have these looks on your faces that I can't tell for sure what they mean. Okay, there's a note underneath here that says the alternating series test, which we abbreviated AST, only tells you if it converges or diverges, doesn't tell you what it adds up to. The only ones we know how to find the sum, for which we know how to find the sum, are the geometric, where we have a formula, or if you take the limit of partial sums, you could do that as well. But that's a long, messy way. And the alternating series test requires that eventually they decrease. So kind of like that last example, they don't always have to start off decreasing, but eventually they have to be decreasing. Because sometimes there's some little wiggle room in the beginning based on whatever your formula might be. So look at my example 1A. How's it different than this example I just did right here? How is example 1A different than that?
Usually not over n.
That one was over n. Someone just said it, I think.
It's n minus
Oh, it's a -1, thank you. It's a -1. How is that series different than this series? One subtle difference.
The n minus 1.
The n-1 versus the n on that -1. This one has an n, that one has an n-1. What does that do to it?
Just the terms are alternating.
It just flips the terms around in terms of which ones are positive and which ones are negative. You still have the 1 over n part, right? I could write it this way. You don't want those -1s to freak you out. It just means it's alternating and it just helps you decide which ones are positive or negative. So this is the only thing that's really different is the n-1. So when you plug 1 in there, the first term will be positive because you get -1 to the 0. So you get positive 1 over 1, and then you'll get -1/2, positive 1/3, -1/4, and so forth. So it's really not much different. But as soon as you see that it's alternating, you can just say, I'm going to use the alternating series test. And you're going to tell me what is the limit as n approaches infinity of the part that's not alternating. What's that limit? Nobody knows that limit?
Zero.
Thank you. Making sure we're awake. That limit is 0. The sequence of 1 over n is decreasing. Right? Each fraction is getting smaller. Therefore, the series converges by the AST. As long as your terms are heading towards 0 and getting smaller, the terms that without the signs, heading towards 0 and getting smaller, it will converge. This is just talking about the sequence of terms. What about B? What about B? One B, same question, wants to know if this series, n equals 1 to infinity of -1 to the n over n squared plus 5. We want to know if that one converges or diverges. What do I want to do? Kind of see. Go ahead.
Separate the part that's alternating from
Yeah, separate the alternating part from the rest of it. So this is the part that makes it alternate right here, the -1 to the n. So if that part wasn't there, we want to know what's happening to the rest of those terms. So if we take the limit as n goes to infinity, I was going to write the whole thing, of the positive part, what's that limit? Here's your hand.
it. It's 1/5.
It's not 1/5.
It's 1.
It's 1, n squared over n squared. If you did L'Hopital's rule, you'd get 2n over 2n, which equals 1. What does that tell us? What does that tell us about this series? In the long run, what do my terms look like?
The ratio is 1 to 1.
It's not a ratio, because I just took I wasn't like the limit comparison, you're kind of on the right track. I just looked at the terms themselves. So these terms, in the long run, are looking more and more like the number 1, is what we're really saying. So if we wanted to start by listing the first couple terms, like the first one, if I plug a 1 in there, I get 1/6, right? So I get -1/6 would be the first one. If I plug a 2 in there, I get 4/9, that'd be positive. So I could plug some numbers in there. But what this limit is telling me is that if you get far enough out here, it's like you're adding 1, then you're subtracting 1, then you're adding 1, and you're subtracting 1. Now, they're not exactly 1, but they're so close to 1 and far enough out there that we're just gonna round them to 1. Why does that mean it diverges?
Every number actually reaches the point 1.
Well, it never reaches 1, but we're worried about what the sum ends up being.
Oh.
So let's say everything up to here added up to 84. Let's just say everything up here added up to 84.
It's 0, like because the adding starts 1 also time.
So it's like we're adding 0, but every other term it changes. So right here, our sum is 84. And if I add 1 more, now I'm at 85. And if I add another one, I'm back at 84. And if I add another one, I'm up at 85. And so forever, my sum is going to bounce to 84, 85, 85, 84, 85, 84. What's it heading towards? See how it's not going towards anywhere? It doesn't have one answer what it adds up to? Because unless you're eventually adding 0, the number's going to change. So because this right here is not 0,
Would that be the divergence test?
you also could have used the divergence test.
Wasn't that pretty much what it is at that point? Because it doesn't equal 1.
Except I didn't include the negative here.
Okay.
So if I had included the -1 in this limit, you're totally right, I would have been doing the divergence test, which also would have been, the problem with the divergence test is the answer would have been, limit does not exist, because it's positive or -1.
Yeah.
This one, because I ignored the signs, is divergent by the alternating series test. You could have used the divergence though as well. If these terms aren't eventually adding and subtracting 0, it's definitely going to diverge because it doesn't add up to one number. Remember, converge means it adds up to something that you can point at, the number on the number line. I thought it added up to 84, so then I got to 85. Then I got back to 84. Then I got back to 85. I don't know what it is. It's either 84 or 85, but it has to be one answer. Good? What about that next one? That next one's not so pretty. Put it right here. -2/5 plus 4/6 minus 6/7 plus 8/8 minus 10/9. I can see that it's alternating. What do you think we should do with it? Carlos wants to rewrite it in a formula maybe, so we can kind of see what's happening to it. So this is good practice. The fact that I see that it's alternating means I'm gonna have -1 to some power for sure. And I'm going to guess that it's -1 to the n. And when I say guess, I mean, I'm just gonna put an n on here, and I'm gonna plug 1 in there and see if I get the right sign. So if I plug a 1 in here, I get -1 to the first power, so the first term should be negative. If I plug 2 in there, I'll get -1 squared, that's positive. If it didn't work, I would have added or subtracted 1 here to adjust just a little bit. Make it look more like this maybe. That just adjusts the signs of where you start. So that one works. And then I see a fraction. Let's talk about the numerators first. What do you see about the numerators?
Multiply by 2.
Multiplying by 2? Not quite, because 2 times 2 is 4, and 4 times 2.
And 2n.
So we're adding 2, so it's 2n. What are you saying, Joseph? Is that what you're saying?
That's what we do add.
We're adding 2, so we keep adding 2 multiple times. 2 times 1, 2 times 2, 2 times 3, 2 times 4. That works. And what is the denominator doing?
Adding 4.
Not adding 4, you're on the right track though. From here to here, I'm not adding 4. So I'm adding 1 each time there. But what were you going to say? What are you adding 4 to? You're right.
Oh, I was just thinking of the A1 plus 4, A2 plus 4.
Okay, so it's actually n plus 4, right? Because if this is the first term, it's 1 plus 4 is 5. This is 2 plus 4, 3 plus 4. So you were right that you're...
In my mind, that's what I was thinking.
Yeah, that's why I figured you were. Technically, though, we're adding 1. So this is really like a 1n right there. That's where that 1 comes from, or just the regular n. So here we're adding 2, so it's a 2n. If you're adding 1, there's a 1n. And that plus 4 is just an adjustment to make it start in the right place. If it had started on 95, it would have done n plus 94, or whatever it needed to be to start there. But the 1n is because it's going up by 1. So you were on the right track, just communicating. So we've rewritten this series. I'm going to erase that one, it's prettier. Now it's the right one. Definitely an alternating series. What do you suggest that I do? Take the limit of what?
2n over n plus 1.
The limit of 2n over n plus 4. So we're taking the limit of the positive portion. That limit is 2. And that is not equal to 0. So it's divergent by the alternating series test. Because what this one tells me is, like that one we just did, in the long run, we're going to be adding 2, then subtracting 2, then adding 2, then subtracting 2. And if those terms aren't heading towards 0, there's no way it can converge. Questions there? Alternating series. Easiest one, you just really have to take a limit. And recognize that it's alternating. Think we're okay there? We're going to do more of this alternating series test as we start 11.6, which talks about absolute convergence. And I'm going to give you my definition that goes with the mathematical definition. So 11.6 starts with absolute convergence. A series is called absolutely convergent because what it's asking is, if everything was positive, would it converge? What if it wasn't alternating? Would it still converge? That's really what they're asking. Does it converge if you take the absolute value of every term? If we go back to this guy. If we took the absolute value of every term and everything was positive, that would be 1 plus 1/2 plus 1/3 plus, everything would be a plus if we took out the negatives. If these were all positive, does it converge? If these are all positive? That's my question for you. What if they were all positive? I'm really hoping that somebody recognizes
Yeah,
it.
because it's harmonic sequence.
It'll be the harmonic series. If those are all positive, it's the harmonic, right? Let's come back and look at this guy. If I take out the negative part and just make everything positive, this is what it would look like, right? If everything was positive, if I took the absolute value of every term. What do we know about this series?
It's divergent.
It's divergent, it's the harmonic series. So when if I was to ask, is this absolutely convergent?
No.
The answer is no, because when I take absolute values, I don't still get a convergent series. Those are my words, so we'll talk about the notation here after our break. Got a little late start though, so we'll do a little before the break, just to make sure we got absolute. I just want to talk about definitions and then we'll do an example. So absolutely convergent means it converges even if everything's positive. Converges even if everything is positive. Those are my words. We've got the fancy definitions there. me today. Absolutely convergent means an alternating series converges even if it's not alternating. Okay, what I mean by that? It's an alternating series, meaning it's going positive, negative, positive, negative. But if you could just make everything positive and it converges, then we call that absolutely convergent. Those are my words. Fancy words look like this. It's what you have on your paper. If you take absolute values and it still converges, then the original series is called absolutely convergent. But that's what I mean by, this one was probably alternating. This is now all positive, so even if it's not alternating, that converges. Similar notation. And conditionally convergent, make sure you understand what the conditionally means. Conditionally means it will converge only on the condition that it alternates. Go back to this guy. This guy was convergent, right? The original one. He converged, alternating, heading towards zero. But when we talked about, let's erase it again, when we talked about the absolute value, it diverged. So this one here, we call it conditionally convergent because it only converges on the condition that it alternates. It's not absolutely convergent, but it's conditionally convergent. So there's three things that can happen. One is I'm going to get a pen that works. That's not one of the three, that's four. There's three things that can happen with an alternating series. Any alternating series could be one, could be absolutely convergent. If the series of absolute values still converges. Could be conditionally convergent. Conditionally means it doesn't converge absolutely, but it will converge if it alternates. Not absolutely convergent, but the series converges because it's an alternating series that's heading towards zero. That's an example of this guy. He's conditionally convergent because if we keep him alternating, he will converge. If we take them off, he won't. And guess what the third thing is?
Divergent.
Yeah, he might just be divergent. Like this one. It diverged by itself, even though it was alternating, it diverged. If it can't diverge when it's alternating, there's no way it's gonna, if it can't converge when it's alternating, it won't converge if everything's positive. So you'll be asked in the section 11.5 and 11.6 about alternating series, about talking about whether or not they're absolutely convergent, conditionally convergent, or neither, if they're just divergent. We really only ask those questions all about alternating series. If it's already positive, it doesn't make sense to take an absolute value if it's already positive. So let's take a break from here, and then we'll come back and do some examples of this, and then we'll learn 2 more tests. We haven't had enough yet. Let's take a good 10-minute break. I've got a few more quizzes to pass back. Okay, let's keep going so we have time to get through these other tests. So we just talked about the definitions of absolutely convergent, conditionally convergent, and divergent, which we've already talked about. So I'm on 11.6. We're going to look at 3 different series and decide if they're, which one of those 3 they are. 11.6, the question is it absolutely convergent, is it conditionally convergent, or is it divergent? You always want to check for these in this order. Because it might be convergent with the AST, but that doesn't help you answer this question up here. This is a stronger question than this one. So you can check this, but that's not enough to know if it was absolutely convergent or not. So the first thing we're going to do is take the absolute values. So we're going to say, all right, what if we take the absolute value of these terms? What series is this? The same one we've been doing, just making sure you've got the notation down. If I take the absolute values, it's now just this series, which is what? The harmonic series, and it diverges. Divergent, harmonic. So the question is this series absolutely convergent? No, why not? You gotta be able to tell me why, guys, otherwise I think you're just guessing, 50-50 chance of guessing right. Not absolutely.
Because it doesn't
Because the
converge when it's
absolute
not
value
alternating.
will-
Perfect, I love that, those words, Nick, or Zach, Nick, whoever you are. Zach is Zach today. He said because it doesn't converge when it's not alternating. What were you saying, Joseph?
I was saying that.
You were gonna say that?
I was getting to that.
We're gonna use slightly different words though?
No, yeah.
There's different ways of saying it. But I love it, that's exactly what we're looking for. When we take away the alternating part, when it's not alternating, it diverges. So, not alternating is the same as taking absolute values. Now, you don't actually have to write this part out, because the question just wants to know which one of these 3 is it. I'm writing this out to make sure you understand what we just looked for. We took absolute values, it didn't converge, so it's not absolutely convergent. So now we're going to check for conditional convergence. How do we check for conditional convergence? Conditional convergence means, okay, if it's alternating, will it converge? How do we check an alternating series to see if it converges?
Take one minute.
Take the limit of
Part which is not convergent.
the, what?
Not the part which is an alternating.
The part which is an alternating. We use the AST, the alternating series test. So it's not absolutely convergent, so now I'm going to check for conditional convergence using the AST. So now I want to say, okay, what happens to the part that's not alternating? That's the part that's not alternating, right? That's equal to 0. Well, what do you know about these 1/n's? Are they increasing or decreasing? Is 1/2 bigger or smaller than 1/1? What happens to these?
Decreasing.
They're decreasing, right? They're getting smaller? So what's that tell me? The alternating series test says
It's convergent.
it's convergent. If that limit is 0 and those are decreasing, and I like to say them together, if they're decreasing to 0, the terms that are not alternating, therefore conditionally convergent. Why is it conditionally?
Because
Convergent. Only when it's alternating. It converges.
Only when it alternates is it convergent. It converges on the condition that you let it alternate. If it doesn't alternate, it diverges. So that's what makes it conditional. So that was, yeah, so I don't have to check for this one because I'm done. I got conditional convergence. Yeah? I think Joseph and Zach are on it. I don't know, the rest of you kind of quiet. I'm like, oh, Chad's there too. Getting a little worried about some of the quiet faces. Let's look at the next one. The next one, same question. Here's an alternating series. Want to know if it's absolutely, conditionally convergent, absolutely convergent, or divergent?
Absolute convergent.
You think it's absolutely convergent? Why?
If we compare it to a P-series.
Okay, so I like what you're saying, but it's not even comparing it to a p-series. It actually is a p-series when we take absolute values. So the first thing we want to do is take the absolute values and see what that series looks like. So when I take the absolute values of this, we take the absolute value of each term, that just takes off the alternating part. So it gives me this series. So this is where Carlos was saying, let's compare it to a p-series. We don't have to compare it, this is a p-series. Okay, we just took off the negative ones because it's not alternating anymore. And so I'm going to just write down what I know about this series. This is a convergent p-series. Because p equals 2 and that's greater than 1. Remember, p-series converge whenever you have a p greater than 1. So we took this alternating series, we turned it into a completely positive series. And what if it's not alternating? It would look like this if it wasn't alternating. And this series converged. So therefore, what do you say about the original series? Carlos said it earlier. Remember the question was this, which one of these three? We just took absolute values and it converged.
Absolutely convergent.
Beautiful. We took absolute values and it converged, which means it's absolutely convergent. It converges even if it's not alternating. It converges if it is alternating too. Was that on the previous page? Make sure I see what that point is. Oh, it's a theorem at the very top that I missed. If the series is absolutely convergent, the original series definitely converges. If it converges if they were all positive, that's even stronger than letting it alternate. So this one is still going to converge by itself too. You don't have to go back and check it. If it converges when everything's positive, it'll definitely converge if everything's alternating. Now you want to be careful when you're working on these homework problems and the lab problems, is sometimes they ask you these three questions, like is it this absolutely, conditionally, or is it divergent? And sometimes they'll just say, does it converge or diverge? They don't really care if it's absolutely convergent or not. So you don't have to necessarily always check for absolute convergence, only if they're asking about that. Agree with that one? Yes.
So you said if the second term is absolutely convergent, the first term or the first sequence is convergent, or it's also absolutely convergent?
So this series is absolutely convergent, which means this series is convergent. That's what I was saying.
Okay.
Because if I hadn't asked for absolute convergence, you could have maybe checked it with the AST or something, and you would have found that it converged. But my point is, once you know it's absolutely convergent, you don't need to check again to see if it converges in its original form. So because this is absolutely convergent, this is also convergent. Because this is stronger than that. So that was my point, though. Sometimes people write absolutely convergent, which isn't wrong, but sometimes I just want to know, does it converge or not? But absolutely convergent always implies convergent. So good questions and statements. I like this clarification. Okay, what about the last one? That one doesn't even look like an alternating series.
The sign is alternating between positive and negative.
Say that again, Joseph, I couldn't hear you.
So but when you graph a sign, it's all sign effect is alternating.
Yeah, that sign portion of it is alternating in a sense. It's not completely obvious that that's an alternating series, but the sign of a number could be positive, could be negative. If you took the sign of 1, we're talking about 1 radian, I don't know what the answer is. And then the sign of 2 and the sign of 3, those answers are all going to be numbers between -1 and 1. And maybe one of them is 0.8, the other one's -0.6. I mean, we don't know what they're going to be exactly. But these do make it alternate. Weird kind of alternate, like you might have a couple positives and then a couple negatives. It kind of depends on where you end up, which quadrant.
But then at that point, if we were to, let's say when tests were absolutely convergent, wouldn't the sign and how would that work out with that?
Okay, so if we're testing for absolute convergence, which is the same question here,
We just take out the
we
sign.
would take the absolute value and say instead of being between -1 and 1, it's between 0 and 1, because it's positive, right? Which is exactly what we're looking at. So to test for absolute convergence, if we take the absolute values, we can't really say much other than this because there's not a nice way to take off the sign portion of it. Which, by the way, when you're testing for absolute convergence, you can go straight from here to here. You don't need to write this step, I'm just showing you what I'm doing here. So this happens all the time where people just take this and rewrite it as this. I can see that you took the absolute value and then you could say it's absolutely convergent. You don't have to write the intermediate step. So the question is, this new series that we have here, does this new series converge or diverge? That's the question. You want to address this like it's a brand new problem. Like maybe it was on today's quiz. What if that was on today's quiz? And I said, does this series converge or diverge?
Converges.
Do you think it converges? Why?
Oh, I did like a sort of comparison thing, it's less than or equal to 1 over n cubed.
He did this sort of comparison thing, which is beautiful. He compared it to 1 over n cubed. Why? Why does that work? We Joseph and I had a little conversation a minute ago about why that is actually true. Because what do we know about sign values?
They go repeats themselves.
Yeah, they repeat themselves and they're always between -1 and 1. So the highest this could ever be is 1. Most of the time it's going to be something smaller than 1. So this term right here is definitely smaller than this term. Because some of these have numbers that are, 0.6 or 0.4 or 0.38, whatever it might be. Because of what we know about sine functions. Whenever you see trig functions, you're going to use the fact that they have a minimum and maximum of 1. Sines and cosines do it. What do we know about this series?
That's convergent,
Why?
because P is equal to 3 versus greater than.
Aha, this is a convergent P series. P is equal to 3, which is greater than 1. So we know that this series is a convergent P series. So what do we know about this series?
That I'd say the absolute convergent. Because that's convergence.
Well, this one's absolutely convergent.
That's what I'm saying.
This one
Absolutely
here
convergent.
is convergent, why?
Because less than or equal to.
But what's test did we use? Comparison test. So this one converges by the comparison test. So when you said I kind of did this comparison thing, you actually were doing the comparison test. Comparison test says if you have a convergent series and yours is smaller than that, you definitely will still converge. Can't head up to infinity if you're smaller than infinity over here. So this series is a convergent p-series. This one converges by the comparison test. The question was, what does this series do? Is it absolutely
It's
convergent? It's absolutely convergent because when we took its absolute values, it converged. So therefore, the original series, n equals 1 to infinity, sine n over n cubed, is absolutely convergent. So even if all the signs were positive, it would still converge. Questions there about notations, words, explanations? Okay, so we got 2 more tests to learn. The ratio test and the root test. And they come up when you have certain types of problems that are usually really messy, and it clears them up nicely. And before we talk about the ratio test and the root test, I'll tell you that really what they are is they're checking to see if in the long run, does this series act geometric or not? Is it kind of acting like a geometric? It might not start off geometric, but maybe when you get far enough out there in the list, it is acting geometric. And that's what we're looking at. So the ratio test says, the ratio test says lots of things. Let me get rid of this. The ratio test says that first you're going to take this limit, which is defined to be this expression. Can someone tell me what that represents, what that means?
Limit of the next term and the current term.
Take some term over the term before it, like, maybe the 7th term over the 6th term. In the long run, you take a term divided by the one before it, but it's way, way out there in your list. So you go out there past the 4 billion mark, and now you're going to say, okay, what happens if I take the ratio of this term over the one before it? And we're going to call that L. Let me remind you about geometric before we go on with what this tells us. Could someone give me an example of a convergent geometric series?
1 over 2 to the n.
1 over 2 to the n. Do we agree that's geometric? Can we list a few terms? What's the first term?
1/2.
1/2. The next one?
1/4.
1/4. 1/8. 1/16. You guys can keep going, right? And is it convergent? Like, right? Why is it converge? What's R?
1/2.
R equals 1/2, and that's less than 1, right? How do we know R equals 1/2?
Because the bottom multiplied by 2 each time.
The bottom's getting multiplied by 2 each time.
And the top's only going up by 1, so it's 1.
But what if I can't recognize
In
that?
order to reach the next term, you need to multiply by
Yeah, to get to the next term, I'm multiplying by 1/2. But what if I'm slow, I don't recognize patterns, and I'm trying to see if it's geometric?
You can take the 1/4 and divide it by 1/2.
Oh, I could take some term and divide it by the one before it. Or maybe I could take this one and divide it by that one. Or this one divided by that. Doesn't really matter which one, right? I'm going to take A4 over A3. I just want to go further out there. I'm making a point here. I know you guys can already see the 1/2. I take this term divided by the one before it. It turns out to be 1/16 times 8 over 1. What do you know? It turns out to be 1/2, which was my R. Okay? So in a geometric, it converged whenever your R was less than 1. The ratio test is doing exactly that. It's just taking some term divided by the one before it. It may not always be a constant. If it's geometric, it's always 1/2. But what we're testing is, in the long run, is it approaching something like a 1/2? Like it's almost geometric. So that's where the rules are and what this tells us about what L is. It's like, what's L? L's just your limit. And the question really is this limit giving you an R in the long run? Is it acting geometric in the long run? If L is less than 1, then the series is absolutely convergent. Why do you think it's absolutely convergent? Why absolutely?
Because it'll be the same.
Here's a hint. We took absolute values up here, right? If you're taking absolute values and looking for an R, you're taking absolute values of everything. So you could just say it's convergent, but it's also absolutely convergent. We really just care if it's convergent. If L is greater than 1, then the series is divergent. So both of these go along with what we know about geometric, right? But the problem is, if L equals 1, it's inconclusive. And the reason it's inconclusive is the limit's approaching 1, but if that R is slightly less than 1 in the long run, that's different than slightly more than 1 in the long run, and we can't tell for sure which one it is. So if you got an L equal to 1, you'd be like, okay, now I can't use the ratio test. But the ratio test is just saying, does this in the long run kind of act like it's geometric? It's not that new, it seems new. We normally use the ratio test whenever you have factorials. You saw some factorials early on, 11.2, 11.3, I can't remember what section that was. It cleans up factorials nicely. My example 2a jumps right in with those, and I'll show you how. So 2a wants to know, does this series n factorial over 5 to the n, does it converge or diverge? Before the ratio test, our options were, well, we could take the divergence test. That limit's kind of hard to take. I don't really know how to do limits with factorials. Kind of weird. I could do the integral test, but I don't know how to integrate factorials either, for that matter. We could list a few terms. It's not geometric. So I'm kind of stuck. So what I'm going to do is, because I see factorials, I'm actually going to jump in and use the ratio test, and I'll show you why it makes things nice. So to use the ratio test, we have to be willing to deal with a mess. We're going to take the limit as n goes to infinity of the n plus first term, which is the actual term I'll get when I plug n plus 1 in there. We can do this. N plus 1 factorial over 5 to the n plus 1. You agree that's my n plus first term? Over the nth term. The nth term is the term they gave us. It will always start off messy, but it will get better. Okay with the notation, what I did? How can I simplify that? I have a fraction divided by a fraction. Yeah, flip the bottom one over and multiply. Let's at least get rid of one fraction. So that's n plus 1 factorial over 5 to the n plus 1 times 5 to the n over n factorial. Now I have these absolute value signs on here, but I can recognize that nothing there is negative ever. So if you just want to drop them when you don't need them, you're totally fine doing that. Everyone agree that we don't need the absolute value sign because everything was already positive? So what reduces here?
I will tell you.
The 5 to the n's are going to reduce for sure, right? I've got 5 to the n up here and 5 to the n plus 1.
So you're just gonna do 5.
So I'm going to have one extra 5. The extra 5 is down here. I just have 1 5 left, right? Because I had one extra 5 here. So I paired up there. And for those of you who are still a little rusty with factorials, I'm going to write out what this means. In this numerator here, n plus 1 factorial means n plus 1 times n minus 1 times n minus 2. It means just keep subtracting 1 until you get all the way down to 3, 2, 1. Right, whatever number you start with, just keep multiplying and subtracting until you get down to 1. So 5 factorial, we start with 5, subtract 1, subtract 1, subtract 1. Okay, I'm good. So that's this part. Here's my 5. N factorial means start with n, subtract 1, subtract 1, keep doing that till I get down to 1. You do not have to write these all out. I'm doing it for those of you who aren't real comfortable with factorials. What happens here?
And factorial is cancelled.
These reduce, right? Look at all of these. Gone. Whole thing's gone. Everything there reduced. This is why we like the ratio test for factorials. So I'm really just left with the limit as n goes to infinity of n plus 1 over 5. What's that limit?
Infinite.
It's infinity, right? Because the numerator is getting infinitely large, divided by 5, it's still infinitely large. That's infinity. Last I checked, that's greater than 1. So what do we know about our series? If your limit is greater than 1, it diverges. Therefore, this original series here diverges by the ratio test. We did the ratio test, we got a limit that was greater than 1, so it's divergent. It actually means that in the long run, these terms just actually keep getting bigger and bigger and bigger. You go far enough out there, you'll see that they do keep growing. It's hard to tell when you look at those factorials. So in the long run, the ratio of one term to the one before it, it's infinitely larger. Each one's infinitely larger than the one before it. That's why there's no way it could convert. This mess will always happen. A lot of people will start the ratio test right here, where they take a term times the reciprocal of the one before it. That way you don't have to write a fraction over a fraction. You can just write a fraction times a reciprocal. It's the same thing. Saves you some space. We'll do that on the next one. Let's look at the next one. Next one is messy. So that one doesn't have any factorials in it, but it sure is a mess. My red's not erasing. N equals 1 to infinity. I have negative 10 to the n, 4 to the 2n plus 1 times n plus 1. Same question, does this series converge or diverge? Again, I don't know if I could do the divergence test, because I've got infinity over infinity. I mean, I've got, it's hard to say what it's going to. See the problem? I don't want to integrate anything like that, that's a mess. I'm really kind of stuck. So I'm going to take the ratio test. I'm going to very carefully take the ratio of the n plus first term over the n term. The first thing I'm going to do is plug n plus 1 in for all my n's. Carefully. Negative 10 to the n plus 1. 4 to the 2 times n plus 1 plus 1. Careful there. Right, I had to put n plus 1 in for the n. With some other stuff going on there. Times n plus 1 plus 1. A lot of n plus 1's going on there. You guys are all feverishly copying. Everyone okay where all the n plus 1's went? So that's just this part. I now have to divide by the nth term. But as I said before, instead of dividing by it, I'm going to flip it over and multiply by it just to save some space. So the nth term is just the way it was given to you. That's the nth term. So I'm going to flip it over. It'll be 4 to the 2n plus 1 times n plus 1 over negative 10 to the n. Messy stuff going on here.
Some stuff cancels.
Some stuff cancels? Yeah, some of it we can see right off the bat that cancels. What is the easiest thing to notice?
4, 2n plus 1.
I don't know if I can see how many of those cancels though until I simplify this exponent.
Minus 10 in power of n.
Yeah, the negative 10s I can see because they just have an n and n plus 1. I can see there's one more negative 10 up here. But these, I think I need to simplify first to know how many extras I have. Maybe you've already done that part, I don't know. But I think I agree with this. This one's pretty clear that I just left with a negative 10 right here. One extra negative 10 up there. But these guys, I need to simplify this exponent to see how many more 4s I really have. I'm going to do that on the next line down. I have a negative 10 on the top. And I have a 4 to the 2n plus 1. And I have an n plus 1. I'm just putting all my numerators together up there on the top. Negative 10, this, and this. Down here, if I distribute and combine like terms, what do I have? 4 to what power?
For the 2n plus 3.
2n plus 3, right? So it's 2n plus 2 plus another one. Times n plus 2 when I simplify that guy. So Zach was right. I'm going to reduce some 4s. How many more 4s do I have down here than up there? Only one more?
2.
2 more, right? 2n plus 3 minus that. There's 2 more 4s down here. 4 squared left over. Subtracting the exponents, I'm left with a 4 squared. 2n plus 3 minus 2n plus 1 leaves you with 2. All right, let's see what we have left. Limit as n goes to infinity of negative 10 times n plus 1 over 4 squared times n plus 2. Algebra's our friend. What'd you say?
As we distribute, can we just simplify it all?
We could distribute, but instead of distributing, I'm going to actually pull the constants all the way out. It'll be easier to find that limit. I'm gonna pull that 10 all the way out, it'll be positive 10 when I take it out. I'm gonna pull this 4 squared all the way out, that's a 16. And then I'm just left with this. N plus 1 over n plus 2, because constants don't change.
As minus 10 over 16.
Oh, absolute value.
No.
What happens to this limit? Right here. N plus 1 over n plus 2? What'd you say, Joseph?
Goes to 1.
It goes to 1, right? N over n, it goes to 1 in the long run? This right here just goes to 1. You can use L'Hopital's rule to get 1 over 1, or you could just look at the highest powers to get n over n.
So we do have this.
So the answer is 10 over 16,
That'd be exactly what convergent.
which is 5 over 8, which is less than 1, which means what, Joseph?
It's absolutely convergent.
Means it's absolutely convergent. This series is absolutely convergent. Absolutely, you can't spell. By the ratio test. What we just found was that even if those were positive 10s, negatives make it alternate, right? Even if those were positive 10s, this series would converge. Now, the question didn't ask was it absolutely convergent. It just asked does it converge or diverge. It's convergent. If it's absolutely convergent, it's also convergent.
So if we put absolutely convergent,
It won't be wrong.
test, we don't have.
That's stronger than convergent. Now, if you put absolutely convergent when it's not absolutely, that'd be a problem, but this one is. So let me remind you what we just found. We found that in the long run, when you take some term divided by the one before it, even though they're all messy and all this other stuff going on, you get far enough out there, each term is pretty much 5/8 of the one before it. Well, not exactly 5/8, but it's pretty darn close. And that's like multiplying by 5/8 each time, which is less than 1 for geometric. So just like the geometric rules, it will converge. Notation's fun, isn't it? A little bit of algebra, a little messy notation. Okay, what about C on the next page? It looks so much nicer than those other ones. Must not be, they look pretty. It's always a scary thing. What about C? N plus 2 over 2n plus 7. Same question, does it converge or diverge? What do you want to do? Imagine when this is on your exam in a couple weeks. All I want to know if it converges or diverges and why. What are you going to do?
If you don't care if it's absolutely convergent, do we have to do the ratio test?
Yeah, we don't care about if it's absolutely convergent, it's already positive, so.
We can just take the limit and do L'Hopital's rule now.
We could maybe just take the limit of the term to do which test?
Do the divergence test. is what
Yes,
we're talking
okay, I
about.
love it. So two things happening back here, back there and up here. So up here, Chad's saying, we don't have to do the ratio test. Just because we just learned the ratio test and it's in the ratio test section does not mean the ratio test is the best way to approach this one. We could do the ratio test if we wanted, but we have a whole bag of other things that we should do. And Joseph's going, don't forget about the divergence test. The divergence test, I've told you more than once, is your best friend. Because if these terms are not approaching zero, infinity, if these terms are not approaching, if I could write them, that would be good. I can't talk and write at the same time. If these terms are not approaching zero, I'm done. What are those approaching?
1/2.
1/2. Not equal zero. What can you tell me about this series?
Divergence.
Diverges by divergence test. Now, if you had decided to do the ratio test for it, because, oh, Jill just taught me the ratio test, it must be what I have to do here. If you'd done the ratio test, you would have gotten 1. You would have gotten 1, which would have told you that, great, we did the ratio test, we did all that work, and now it's inconclusive, meaning I still don't know if it converges or diverges. So if that had happened, you still would have had to do a different test. So you want to start, number one, you want to do a lot of practice, so you start recognizing different things. But you want to start trying to recognize when each test is better than others. And it's not a hard and fast rule. The integral test I only use when it looks like something I can integrate. The divergence test I almost always do either in writing or in my head, because if those terms aren't approaching zero, I know I'm done. So I almost always will do a quick glance. When are those going to zero? If I'm not sure, I'll actually do the divergence test to check. If they are, then I'll try something else. Sometimes you do the inconclusive thing, and you get kind of stuck. I also would have maybe compared it to the harmonic. Well, not the harmonic. I would have compared it to this, actually. I would have compared it to that. Right? Just take the highest powers. But that's a divergent series also. We're just adding 1/2 forever. That's not equal to 0. If I give you $50 every year forever, you are not going to ever run out of money. It's not going to stop growing. So there's all kinds of different ways to approach it. Yes?
Do you care which way you use on homework? Or?
No. You could use any or all of them. So on an exam, I will see 4 different approaches. One person might use the alternating series test. Somebody else might use the divergence test. Somebody else might use the ratio test. They will all give you the same answer if you're doing them correctly. So it's really about which one you see that applies and which one actually works nicely. Because sometimes one or the other just is a mess and it's not your best friend. So it kind of depends. Good question. Okay, let's look at one last test. It's really the same test in disguise again. Remember the geometric that Mike gave us a little bit ago when I was reminding you about geometrics? I think this was the one you gave me. Is that what it was, Mike, to the end? So any kind of geometric we knew was some r to the n, right? That's how we kind of recognized when we had something geometric. Like maybe you had a times your r to the n, something like that. We saw different things like that. What happens when I take the nth root of this 2 to the n that Mike gave us? Nth root. Oh, sorry, 1/2 to the n, 1 over 2 to the n. I lost my 1/2. It'll equal 1/2, right? It gives you that ratio. Because a geometric series, if I can speak clearly, always has powers of your r. So if you take the square root of the second term, you're going to get that you'll get r right back because you've multiplied it twice. If you take the cube root of the third term, you'll get r because you've multiplied 3 times. So what the root test is doing is saying take the nth root of the nth term, and this is just like your r again from the ratio, from the geometric series, if I can say it right. And it's the exact same conclusions. So if you look at the root test, it says the same thing. It says, you can either take this ratio test, or you can take the limit as n goes to infinity of the nth root of the nth term, and call that L. And then we have exactly the same conclusions because it's doing the same thing. The reason we like the root test, it's very rare actually, is when you have nice powers of n that you want, nice exponents of n that you're trying to get rid of. Like I wouldn't take the nth root of this because it would just make it a mess and I couldn't simplify it. This simplified nicely, right? But if I took the nth root of this, I couldn't simplify that. So look at example 3. It's a perfect example of when you want the root test. So example 3 is the series n equals 0 to infinity of this nice messy fraction, all raised to the n. So as soon as you see this giant n out here, or if everything in there was raised to the n, sometimes it's done little different pieces, that's a pretty good sign that you want to use the root test, because that will get rid of that. So to use the root test, we'll take the limit as n goes to infinity of the nth root of this whole term the nth root of the nth term. What plays up nicely there? I end up getting rid of the root and the n over here, right? That's why we do it. So I just have the limit as n goes to infinity of everything else. Oh, by the way, I forgot to put the absolute values on my root test. Forgot to put my absolute values here and here. The reason you need absolute values on your root test is you don't want to take like a square root of a negative, right? That'd be all bad. So we have absolute values here. What's that limit? 3/7. Just look at the highest powers. Negative 3 over 7, but that's absolute value is 3/7. So that's like my common ratio. In the long run, this series is like multiplying by 3/7 each time to get to the next
So
term.
it's absolutely convergent.
So that's less than 1, and it's absolutely convergent by the root test. Do me a favor and pull this handout out if you have it, and if you don't have it, I'll give you another one if I want to talk about it for like 3 minutes, 2 minutes. Everybody has one? The one. Okay, so you're not going to use this on the exam, but you are going to use it for reference. And the more you can tie things together, the less you're going to feel like you need to keep referring to it because they all have very similar rules. The first one, hopefully you changed it to divergence test where it says nth term. We talked about that last time. The divergence test we've been doing, you've got geometric series, you've got p-series, integral, comparison, and then down at the bottom you've got ratio and root that we just did, alternating series from the previous section, and the very bottom one is just saying that if you take absolute values, then that's testing for absolute convergence. And that's that theorem. If it converges absolutely, it also converges. The important thing, though, are these comments over on the right. It tells you when you might want to try each one. So if you look, for example, at the ratio test, it tells you when it's inconclusive, but it says it's useful if you've got factorials around powers. And then the root test is useful if you've got n powers. And then there's other things like, I don't know, the integral test. You have a function that's easy to integrate. So you want to start recognizing and learning when each one is useful so that when you see the next section that we're going to do next time, where all of these series are all mixed up in one section, you know how to approach each one. Because that's really what the next test is gonna be. You know, all these different series all mixed together, and you wanna go, oh, look, this one's alternating. I know I can do the alternating series test. Or this one kind of looks like a P series. Maybe I'll do a comparison, whatever it might be. So use this for reference as you're working. When I see you on, what day is this, Tuesday? On Thursday, we're doing 2 sections. 11.7, if you look in your notes, there are no notes for 11.7. There's just a lab. Because 11.7, there's nothing new. It's really, here's a whole bunch of problems all mixed together. Can you do them? So we're going to have a little bit of a quiz and a little bit of conversation about that, talk about 11.7, and then we'll move on and do 11.8 for the second part on Thursday. Again, as you're working on your lab assignments and getting ready for your quizzes, make sure you read through this too so you understand what's expected for notation. Don't just write the answers, because I gave you the answers. I need to know why. You have a 50-50 chance of guessing the right answer. I'll see you guys in the lab if you're going to the lab.